Stop worrying about homework and start learning with confidence. This is Ask Learn. Complete help for every subject. Like, share, subscribe for daily learning videos.
Alright, so for this problem, the situation is that we have a particle, a charged particle, and it's centered at the origin for a three-dimensional axis. So we have our z, we have our y-axis, and we have our x-axis. And we have, so this is a three-dimensional axis here, negative z going down, negative x going to the left, and negative y coming out of the page. So positive y goes into the page here. And we have three fields. We have one electric field, E, and that's in the positive x direction. We have a magnetic field also in the positive x direction. I'm going to call that one, unsurprisingly, Bx. That's the magnetic field in the x direction. We also have a magnetic field in the positive y direction, so into the page. I'm going to call that By. So we have an unmoving particle here at the center, at the origin. And we have these three fields. And we want to find, in part A, we want to find the magnitude and direction of the force on the particle. So we have two different types of forces here, or we have two different types of fields causing forces. So we'll need the equations for both of those. Force for electric field is an easy equation. The force is equal to the charge times the electric field. That's another thing we're given here is the charge Q. We know the charge. It is a positive charge. So this is easy to calculate. For part A, we have no speed. Oh, I'm sorry, A. For part A, we have V equals 0. No velocity. Oh, we need to have our other equation here. So we have magnetic field force is equal to charge times the velocity times the magnetic field sine of theta. Sine of the angle between the traveling velocity and the magnetic field. Those are the two vectors in this equation. Velocity and magnetic field. Those are the universal sign for a vector. Q is a scalar quantity. So now back to part A. We have no velocity. The particle is stationary here. So for the two magnetic fields, By and Bx, we have no velocity, which means this V here is 0, which means the force is 0. We can't have a force from a magnetic field unless we have a moving charge. So we have no forces from By or Bx. E, however, does not have the same stipulation. There's no V in this equation. So we can find Fe, the force from the electric field, is simply the charge times the electric field. QE. Now what about direction? The force and electric field are directed in the same direction, positive x-axis. So we have our direction here is positive x, which relevant to this problem, the positive x-axis is to the right. This grid here shows that you can define an axis any way you want. We could have the x-axis flowing out of the page, or we could have the negative x-axis pointing down. It doesn't matter. It all depends on how you define it, and then you have to stick to it. So we have positive is to the right for x, which means everything we do in that direction has to be positive. And same for positive y. It's backwards into the page, which means everything in that direction has to be positive, as far as this problem goes. So that's part A. The only force on it is from the electric field, charge times the magnitude of the electric field, and the force is in the same direction as the electric field, which is in the plus x direction. So that's part A. For part B, we have a velocity now that we're given, v, and we're told v is in the plus x direction, which means moving to the right. So let's take a look here and see which one of these, see how many of these fields will affect it. So for E isn't dependent on any factor of sign, so E isn't going to be eliminated. We'll have the same number here. Our velocity is in the same direction as E, or as our field for E is in the same direction as the velocity. Which means, because we have a sine of theta here, that this bx is parallel to v. And when we have a parallel velocity to our magnetic field, parallel means that theta here is 0. Or if it's anti-parallel, it would be 180. But in either case, sine of 0 and sine of 180 is 0. So there's no force from this bx quantity. So the forces that we have, the total force is equal to, I'm going to call it Ft, is equal to By. We have a force from the y, because by the right-hand rule, we have our thumb pointing in V, which is along the positive x-axis, our fingers flat and pointing in the direction y, which means we'll have a force up from this By. By will be up, and we'll have a force E pointing to the right. So we'll have two forces. Bx will be 0. Because for the case of the y traveling into the page, and the velocity traveling along the positive x-axis, they make a right angle. So they are perpendicular, which means we have sine of 90 degrees, which is 1. So that one will give us a force. So our total force is equal to By plus E. We could call it Ex just to keep with our subtext here. The electric field in the x direction, which is the only electric field. That's just simply the force here. And that will be the same because we have the same charge and we have the same electric field. Velocity doesn't play a factor into the force caused by the electric field. If the velocity were changing, then we would have an acceleration and we'd have an outside force other than what we have here. But it's a constant velocity, which means there's no outside force. So that doesn't affect our force here. So this is the same thing we calculated in part A, this Fe. So we know that one already. Now we need to find this By. So what does By? By is the force from the magnetic field in the y direction. So this is Fy. And that's what we need to find using this equation. We have our force due to the magnetic field in the y direction is equal to charge times the velocity times the magnetic field. And we have all of those. So this is something we can calculate. This is By. only the magnetic field in the y direction. And we know what that is. So now we can find our F total here. F total force due to a traveling velocity in the positive x direction is the force from the electric field, F of V, which we have here in part A, charge times the electric field. Let's keep it consistent with how we wrote it. We have that plus By, or Fy here, this Fy, the one we just calculated. Force from the y magnetic field plus force from the electric field. I'm sorry, plus force from the electric field. So it's this number plus this number. And that's our solution for B. Now we have one more scenario here, part C. Now instead of the particle traveling in the positive x direction, it's traveling in the positive z direction, which means our bx will no longer cancel, because now it's perpendicular to both by and bx. Speaking of directions, let's go back here. We'll probably need directions for this F total. So we have this force from the magnetic field in the y direction. Once again, we're going back to part B. So By, for the right-hand rule, we determined points up. So this is in the positive z direction. And we already know this direction is in the positive x direction. So those are the directions for those two forces. What this will do actually is split down. It will travel in the zx plane here. The angle will depend on the magnitude of these two numbers. But this is all you have to put. The force from the magnetic field in the positive z direction due to the right-hand rule, and our force from the electric field in the positive x direction. Okay, that's all finished. Let's go back to part C. So we have a velocity. It's actually the same as it was in part B, same number, but it's pointing up in the positive z direction instead of in the positive x direction. So we'll need two equations now, but the value, the magnitude of this v doesn't change, and it's still perpendicular to y. So that means the magnitude of this Fy is going to stay the same, but the direction is going to change. So let's do that first. So now for By, we have our thumb pointing in the direction of V, up, fingers flat and pointing in the direction of By, into the page, which means our force from the magnetic field in the y direction is going to point in the minus x direction. It'll be opposite the force from the electric field. Which means now these two numbers that we calculated, so let's write another total force. So the total force for part C we've just determined is the force from the electric field, which will also stay the same. None of those numbers change once again. So F of V is the same in all three parts, part A, part B, and part C. That's in the positive x direction. But we have now our force from By in the y direction is in the negative x direction, which means these need to be subtracted. This is why keeping track of your directions is important, because now we have a minus sign here. And now we need to find the direction from the magnetic field in the x direction. So right-hand rule, once again, thumb up, palm flat, or thumb up, palm, fingers straight, palm pointing back. So that means we'll have, at this point, of force into the page in the same direction as the positive y-axis, which means that our bx, or our force from the x direction, will not be related to these two. So these two you can subtract, but the part from the x direction of the magnetic field will be independent because it's in the positive y direction. So now we have this force from the magnetic field in the x direction. This is in the positive y. The force is in the positive y direction. It's due to the magnetic field in the x direction. So basically what this part here in the x direction is saying that whichever of these two forces is stronger is the final direction that it will go in. So if this electric field force, the force due to the electric field, is stronger than the force due to the y component of the magnetic field, it will be in the positive x direction. Otherwise, it will be to the left in the negative x direction. And we know these two numbers already. You can plug that in and find out what that number is. We need to find this Fx, or the force due to the magnetic field in the x direction. So once again, we have our force here for magnetic field. The velocity is traveling 90 degrees to the magnetic field, which means that it will be a sine of 90 degrees, which is 1. So we can discount that. So we have the charge times the velocity times the magnetic field, and those are all quantities that we know. So the force due to the y component of the magnetic field will be, we have the charge, simply the charge of the particle, which is also the same in every case, velocity, which we know, times by. I'm sorry, this is Fx. You already found by. So this is the part for the force of the magnetic field in the x direction, bx, which is this number here. So this is the x direction component of the magnetic field. So this will give you Fx. You plug that in here. Right-hand rule tells us that's in the positive y direction. So that will give you the total force. So there's two ways you can write out the answer here. You can write them all with their directions. So you can have it as your force is equal to, we have the electric field force in the positive x direction. We have the force from the y component of the magnetic field in the minus x direction. And we have the force from the x component of the magnetic field in the positive y direction. Or you can write it like this. These are both two separate ways of writing the same thing. And this here is the final answer.